Alright, so let's start our discussion by recalling what we found recently. We proved that two permutations in Sn in the symmetric group of degree n are conjugate if and only if they have the same cycle structure. And in fact, this led to the conclusion that the number of conjugate classes in Sn equals the number of partitions of n. So we are now going to see another application, actually two applications of the same type of this fact. I mean, besides knowing that there are that many conjugate classes in Sn, as many partitions n has, besides that fact, we are now going to see something else that comes from this. Okay. Consider the transposition 1, 2. That means this 2 cycle in Sn. Suppose we want to know precisely what elements in Sn commute with this. In other words, say we want to know what the normalizer of this element is. We want to determine the normalizer of this. Now, if we think about the normalizer, so that consists of precisely those elements in Sn that commute with this 2 cycle. Now, we already know some such permutations that would commute with this 2 cycle, and they are those permutations that leave both 1 and 2 fixed. That is, they do not change either 1 or 2. And as such, if we factorize such a permutation as a product of disjoint cycles, then these 2 symbols will not appear there. Obviously, any permutation in Sn that leaves both 1 and 2 fixed will commute with this transposition 1, 2, and hence will belong to the normalizer of 1, 2. But besides that, there is another thing that also commutes with 1, 2, that is 1, 2 itself. Also, this itself commutes with 1, 2, or the same thing, that this itself belongs to the normalizer of 1, 2. Now let us count the number of such elements which leave 1 and 2 fixed. That is, let's see how many permutations we have in Sn that fix both 1 and 2. That means any such permutation will be a permutation of the other symbols effectively. And how many other symbols are there in Sn besides 1 and 2? I should not say in Sn, but in the set of symbols on which Sn acts. 1 and 2 are these two symbols. Besides them, we have n minus 2 other symbols. So, the number of permutations in Sn that leave both 1 and 2 fixed is n minus 2 factorial, because that many symbols are there that can be permuted. Now, this implies that we have at least 2 times n minus 2 factorial elements or permutations in Sn that commute with 1, 2. In other words, the order of the normalizer of 1, 2 is at least this, at least this. But where is this 2 coming from? 2 times n minus 2 factorial. So this number is at least 2 times n minus 2 factorial. So to understand where this 2 is coming from, we have to take into account this element also. You see, any let's just give this symbol, this permutation some name. Say tau, this is an element in Sn that leaves both 1 and 2 fixed. The number of such elements is n minus 2 factorial. The number of such taus is n minus 2 factorial. But along with this tau, if you consider this also in the product form, that is, if you consider this type of permutations, that will also commute with 1, 2, because this one does and tau does. So what I am saying is that 1, 2 times 1, 2 tau is equal to 1, 2 tau times 1, 2, right? And so the number of the total number of elements that we have here is actually twice this number. Only the taus give us one class of such permutations, but 1, 2 times tau gives us another class of such permutations. So the total number is twice of this. Now you may be wondering, where does this 1 comma 2 itself come in this list of permutations? That comes because you can take tau equal to E, the identity permutation in Sn. Why? Because the identity permutation also leaves 1 and 2 fixed. In fact, it leaves everything fixed. So in particular, it also leaves 1 and 2 fixed. So for this choice of tau, 1 comma 2 itself appears in this list. Okay, so at least this many elements we are getting in the normalizer of 1 comma 2. But now we can use our counting principle, okay, to see is this really equal to the number of elements? That is, it's not just greater than or equal to this, but is it really equal to this number? That we can now see. And I'm saying our counting principle because we know precisely how many conjugates this 1 comma 2 has. That we know because the cycle structure of this 1 comma 2 is 2. That means it has only 1 2 cycle. So the conjugates of 1 comma 2 in Sn are precisely all the 2 cycles. So we just have to count up the number of 2 cycles in Sn. And that number is related to the order of the normalizer. In fact, if we multiply that number with the order of the normalizer, we should get the order of Sn itself, that is n factorial. Now, the conjugates of 1 comma 2 in Sn are precisely all the 2 cycles or all the transpositions. And there are, how many of them are there? N choose 2. There are n symbols, out of which you can choose 2 symbols to create a transposition. But why are we counting the number of combinations? Are we not supposed to count the number of permutations? Yes, but we know that this 2 cycle is actually the same as this 2 cycle. So for 2 cycles, the order in fact does not matter. So that's why we have combination. So from our counting principle, we are going to have this. Order of the normalizer of 1 comma 2 should be equal to the order of Sn divided by the number of conjugates. Actually, it's expressed in the other way, that is, the number of conjugates is this time this divided by this, but we can write in this way also. Okay, so what is it that we are ultimately getting? N factorial. This 2 can be taken in the numerator divided by n times n minus 1. But that just becomes this. So you see that the order of the normalizer is actually equal to this. But we have already found at least that many elements in the normalizer. So they are the only elements in the normalizer, and as such we have in fact found all the elements in Sn that will commute with 1 comma 2. Thus, the elements in Sn that commute with 1, 2, they have a form R of the form 1, 2 to the power I times tau, where I is either 0 or 1, giving us those two lists, and tau is an element in Sn that leaves both 1 and 2 fixed. So we have not only found how many such elements are there that will commute with 1, 2, but in fact we have actually found those elements, not just the number, but in fact the general form of the elements itself we have found. So that is one thing, and a similar thing can be done for an n cycle in Sn. Consider the n cycle in Sn. The author claims that the elements in Sn that are going to commute with this n cycle again are precisely the powers of the n cycle, nothing else. Clearly, the powers means all integral powers. Actually, there are going to be n distinct integral powers because any such n cycle has order n. Clearly, the powers of this commute with the n cycle, which just follows from one of the rules of exponents. But now the claim is that they are the only elements to do so, where again we are going to take the help of our counting principle. We claim that these powers are the only elements in Sn that commute with our n cycle. Since the order of the n cycle is n, the above powers are n in number. Right. So that means we have already found n elements in Sn that commute with this n cycle. Okay, these powers, integral powers. But now let's see how many conjugates this n cycle has, and from that and from our counting principle we will be able to know precisely the number of elements in the normalizer of this n cycle, that is the number of elements that commute with the n cycle. Now the conjugates of these are precisely all the n cycles in Sn. This is just one n cycle, there will be others. And we now need to know how many n cycles there are in Sn. And that number equals the number of distinct n cycles that you can create from n distinct symbols, and that equals the number of cyclic permutations of n objects, which is n minus 1 factorial. You keep one of them fixed to maintain the cyclic order and then permute the others. So these are precisely all the n cycles in Sn, and they are n minus 1 factorial in number. So since we know how many conjugates there are now, we can calculate the order of the normalizer of this. So this will be equal to the order of the group divided by that number, the number of conjugates. And that number is n. It turns out that the order of the normalizer should be equal to n. But we have already found n elements in Sn that commute with the n cycle, namely its powers. Hence, the elements in Sn that means our claim has now been established, that commute with the n cycle are precisely the powers of the n cycle. And with this, the section itself ends. After this, we have the exercises which we will solve. We will start solving in the next group theory update. And the video also ends here. Our next update is this coming Friday. And on Friday, what should we do? So this is group theory. So let's go to field extensions. Okay, so see you on Friday with field extensions. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.